Okay, let's get started. So, several announcements. First, like I said, we're going to have several paper presentations, and every graduate student or honor student, if you want to do an honor contract, you have to present a paper in this class. So I will send out a doodle link today, and with some other instructions. First come, first serve. And probably next week, I'm going to forward the link to all the students. So undergraduate students, you can also volunteer to present the paper. So this is what happened last year. Some undergraduate students actually enjoyed that. And if you volunteer to present a paper, you don't have to do the paper report. You don't have to write a paper report, and you will get extra points for that. So everyone else, if you are not doing a paper presentation, you need to finish your paper report, and the deadline will be a month from now, and I will send out instruction early next week. We will have our first midterm February 16th. I know so far you haven't learned anything, so but we will have our first midterm there, and also the same day, I invited a guest speaker because it's the day you're going to have an exam, so I'm not going to give a lecture. So I invite a speaker from a government agency. To be honest, I don't even know which agency he is working for. So he graduated from our lab as a PhD student and joined this agency, and never told me what's the name of the agency. So last week, we started some basic knowledge of computer forensics. We talked about the difference between private investigation and public investigation. We started some legal implications, rules of evidence, chain of custody. We also studied a little bit of hash functions. We had an in-class exercise. You tried to partition a disk and also use tools like DD and FTK to extract the image of the disk. So starting from this week, we are going to talk about very technical stuff. Like I said, this class is very application-oriented. I'm trying to organize it in a very systematic way. Talk about lower-level stuff first, then moving up to application levels. So today we're mainly talking about disk forensics. So to do that, you have to understand how hard disk drives work. And of course, there are a lot of new technology now. There are SSD, and there are other kind of media storage as well. But we will study the foundation, how hard disk work. And we will also study how a PC boot. Probably you picked something up from operating system class or computer architecture class. But what I'm going to show you were directly related to forensics and also hard disk. So one of the most important parts in hard disk and also how a PC boots is the first sector of any hard disk. And there is code there, and there are also some records. We're going to study the code, obviously assembly code, and we'll also study the records for volume analysis. So if we have time, we will move up a little bit to file system analysis. So today there is no in-class exercise, but while we study today, next week we are going to do the in-class exercise. So here is like the bigger picture for different layers of forensic analysis. At hard disk level, so hard disk is like the main storage media. Usually we analyze for some forensic results. So at the lowest level, we have this called a storage media analysis. Basically, we are talking about the physical characteristics of the storage media. So obviously, a CD-ROM is different from a hard disk. It's different from SSD. So we need to know how they work. From there, usually there is a level up. There is a called volume analysis. There are partitions on hard disk. Sometimes they are called volumes. There is a slight difference between partition and volume. We will talk about it later. So in each volume, there can be different file systems, and that is called file system analysis. Obviously, after you understand the file system, you can look into some specific files. And memory analysis, memory forensics can also be classified as a storage media analysis, but it's a different storage media. RAM is different from hard disk. So today we're going to cover at least these two layers. Storage media analysis, basically hard disk, flash cards, and usually those storage media, they are organized into several partitions or volumes. And a partition or volume is basically a collection of storage locations that a user or application can write to or read from. So on top of that, on top of a partition and volume, there will be file systems. And in a file system, there can be database, there can be struct place, there can be any kind of files. And the volume analysis is about how we can determine where the file system or other data are located. Because this is not a, so where we're talking about still on the hard disk. We're not talking about the internet. We're talking about where in a hard disk there are probably multiple volumes, multiple partitions, and each of them has a file system. So there will be information to locate where each those file system resides. And also, where you're going to use volume analysis to determine where we can find hidden data. Sometimes with volume analysis and file system analysis together, because sometimes it's also related to how the file system handles things. And the file system is basically a collection of data structure that allows application or the operating system to create, read, and write files. So obviously, we need to understand the meaning of files and the operations on files. We may not be able to cover this part today, but we may have enough time. So the file system analysis, what we're expecting the results can be the file content, data fragments, and also a lot of metadata associated with all kinds of files. So, like as I think I mentioned in the first class, a lot of information about file, like the time, the modified time, query time, those information are not directly stored in the file content. It's not part of the file content. It's actually some metadata saved in the file system. And if we understand the storage media, we understand the volume, and we already understand the file system, then we can move up to application layer. We can do some specific analysis for different applications. So in this class, we will do some image analysis, we will do image forensic analysis, malware forensic analysis, and you can see that when we handle those issues, we're not directly thinking about hard disk or partition anymore. But we probably need the knowledge from hard disk file system to extract those files in the first place. But after we extract those files, we can use some application-specific knowledge to understand those files. So the first part of today's class is to understand disk drives. First, we will study the geometry of hard disk. several concepts. The first one is called head. Basically, it is an arm or a head. It's a physical device that can read and write data to a drive. Actually, it writes and read data to a drive planter. And track is the concentric cycles on a disk planter. Cylinder is a column of tracks on the disk planters. And the smallest unit on a hard disk usually is a sector. Sector is a section on a track. And obviously, the smallest unit you can read and write is byte. But the collection of several bytes, usually 512 bytes, is called a sector. And usually information is stored in a sector unit. So here is some pictures. So this is a hard disk. You can see that there are 3 disk planters on this hard disk. And there is that arm is called a head or head arm. That is a device to actually read and write to each planter. So some of the hard disk, each planter has 2 surfaces, right? So some of the hard disk, both surfaces, they can be used to store information. That's why there is a head above each planter and also at the bottom of each planter. And the very interesting thing about this traditional hard disk is you can see that, for example, there are 3 planters here. So if we can write and read to both surfaces, there will be 6 heads or 6 arms. But those 6 arms, they are grouped together. So you cannot just move one head. It's not physically not possible. So we will go back to that issue again. So each planter is divided into concentric rings, and those concentric rings are called tracks. And each track is further divided into these wedge-shaped areas, and those are called sectors. So usually a sector is 512 bytes, but this is hardware specific, implementation specific, not necessarily the size. But what we're going to study today, one of the data I actually dump a physical hard disk is 512 bytes. So going back to here, you see that the heads, the arms that across the planters, they are actually locked together. So it's an assembly of head arms. So this means that all the heads, they move in and move out together. So each head is always located at the same track number. So even though those heads, they are on different planter, but they are always located at the same track number because they move in, move out at the same time. So it's not possible to have one head at track 0 on planter 1 and another head on track 1000 on planter 2. That's physically not possible. So because of this design, often the track location of the head is not referred as a track number, because instead we call it as a cylinder number, because every head is at the same place anyway. So cylinder is basically this 3D, is a set of all tracks that all the heads are currently located at. And this is this three-dimensional concept. So if we give you a hard disk like this, we tell you how many heads are there, basically telling you how many heads are there, you can figure out how many planters are there. There are 2 different cases. If it's a single phase planter, then obviously 1 head per planter. If there are both phases can be used to store information, then 2 heads per planet. Then the number of cylinders is basically the number of tracks on each planet, and also each track there is a fixed number of sectors. So in this example, we can see that there are 1,024 tracks on each planet. Then there are 32 heads, and each track has 63 sectors. That's why this hard disk has more than 2 million sectors. And each sector is 512 bytes, so this hard disk is like 1 GB. So after we understand how this works, obviously we want to address the content on a hard disk. And there are 2 ways to address the sectors on a hard disk. The first one is called the CHS address or addresser. C is a cylinder, H is a head, and S is sector. So the cylinder number starts with 0. The head number starts with 0, but the sector number usually starts with 1. So the first sector on any track or any planet is called the sector 1. However, the first cylinder is called cylinder 0. You don't have to remember those actually, but this is just traditionally how they use this addressing. So there is another, so you can see that this addressing is 3-dimensional, it's X, Y, Z. And there is another way is to transform this address to a 1-dimension number, and that is called a logical block address. And this address starts from 0. So obviously, the first sector on the first cylinder of the first head is the first sector also in this logical block addressing. But it starts with 0, so it's LPA 0. So there is a simple equation to calculate this. How can we get the LPA from the cylinder CHS number? So I'll give you an example here. So we have a disk with 16 heads per cylinder. Each track has 63 sectors. So we have the address cylinder 2, head 2, sector 4. So we want to calculate its logical address. So we basically just put those parameters into the equation, and we can calculate the number. So this will be in one of the exams, but you don't have to remember the equation. I will give you the equation. But you still need to understand how it works. So the second part I want to talk about is how does a PC boot? It sounds like we're talking about totally different issues. We just talked about how hard disk work, now moving to how PC work. I promise you they are very related, and probably in an hour you will understand how they connect. Okay, why do we need a boot anyway? The basic reason is hardwares, all hardwares, they don't know where the operating system is. And they don't know how to load the operating system, and obviously they don't know about the applications. It's the operating system job to load the applications. And hardware, the CPU, the memory, they can be used when the hard disk is changed. So you don't have to use the same hard disk, you can still boot the computer. So there is a mechanism that for the hardwares to know where to load the bootloaders from a hard disk, and the bootloaders will know how to load other operating systems. So there is a special hardware to do this job, to do this bootstrap loading job, and that's called BIOS. But obviously, I'm talking about PC here. So modern smartphones will have a slightly different architecture, and smartphones, they don't even have hard disk anyway. So the boot process is a little bit different. And usually smartphones, they don't have BIOS. So actually, for my research, I do smartphone or IoT-based research more than PC-based. So I use ARM architecture more than Intel architecture. So in the ARM architecture, we don't really have BIOS, but all the PCs, they still follow this structure. So the bootstrap loaders, the BIOS, will usually do some test to check all the physical devices is in a right state, and they try to locate the kernel and also load the kernel to the main memory and start execution. So if you remember that, you cannot run any code directly on hard disk. Anything you run, you have to load to memory first. Of course, there are like room. Room is not really RAM, like a BIOS. BIOS is not really RAM, it's usually room. You can directly run code on BIOS. So CPU can directly run code there, but CPU cannot directly run code from hard disk. There is no way for CPU to do that. So in some systems, a simple bootstrap loader will fetch a more complicated bootloader from the disk. And that bootloader will load an even more complicated bootloader and eventually load the operating system kernel. And the operating system kernel will load other applications to run. So when does this and how does this boot process occurs? So basically, whenever you reset your computer, no matter you physically reset it, that will trigger an interrupt. So you all took operating system class before, right? So you know what is the interrupt. That will trigger an interrupt. And that interrupt will cause the instruction register to be loaded with a predefined memory location. So every time you do that, the IP instruction register will enter a predefined state. And at that memory location, there is only one instruction. Basically, it's a jump instruction that transfer execution to a bootstrap program, to BIOS or something. So this program, if it's BIOS, is usually stored in ROM, not RAM, because then at that moment, when you reboot the computer, you haven't loaded anything useful to the RAM. So everything in the RAM is just, could be garbage, could be something left from last time. You don't know what is there. It's not in a safe state. So you give the control to the program, which is stored in room or BIOS. And so usually the BIOS will do the following tasks. It will first run some tests to determine if the memory is good, the CPU is good, all the hardwares are good. And it will also, after that, it will go through a predefined list of devices until it finds one that is bootable. If it cannot find such device, it will give an error and the boot process will stop. And it will also initialize CPU registers, device controllers, and some other system registers before it gives control to the operating system. So this is usually what you see. So if you use PC, you should be familiar with this. You can choose a lot of devices you want to boot from. Usually the BIOS will set CD-ROM first. So whenever you put, like for example, when you want to install Windows operating system, you put a Windows CD-ROM there. Then that CD-ROM, the disk, is bootable. So the BIOS will check that, find how this disk is bootable. So I'm booting from this CD-ROM instead of the hard disk. That's how the operating system installation process gets started. And if the CD-ROM is not there, or the CD-ROM itself is not bootable, for example, you put a music CD there, the BIOS will check, oh, this is not bootable. Then I'm going to the next device to check if it's bootable. And usually that device will be a hard disk. And in hard disk, they will check how many partitions are there, which partition is bootable. We will talk about that later. So this is also a picture I took from online. So this is a BIOS checking all the available hardwares and if they are in a safe state. That's a self-checking process. So if the bootable device is a hard drive, so on finding that bootable device, the BIOS will try to load and execute its boot sector. So can you guess which sector is the boot sector? Just guess. The first sector? Yeah, so obviously it should be designed as the first sector. So that's how we collect everything together. We're talking about there are so many sectors on a hard disk, and the first sector, it has basically two things. One is called the master boot record. We will study this later, and also some binary code there. So the BIOS will just load that sector to the memory, then give the control to that code. Then obviously BIOS will not be executed again. So that code, usually I call it MBR code, but technically the MBR is actually the table part. So the code in the first sector, you will check the partition tables. You will check the MBR for any active partition. If it finds any active partition, it will try to load that partition's first sector. But that partition's first sector is not necessarily at the same place for different hard disks. So the master boot record is always located at the first physical sector of a hard disk. But each partition, because the partition size will be different, their first sector may be at different locations. So that's why there is a master boot record to tell this piece of code where the next boot sector is, and you should know that. So the boot sector is usually operating system specific, and but most operating systems still they use this process. But like I said, this is related to hard disk. If you are using a mobile phone, the boot process is different. So if there is no active partition or the active partition's boot sector is not valid, the MBR will load a secondary bootloader and give control to it. The secondary bootloader will select a partition and load its boot sector. So there are some examples, like I guess probably you use this like GRUB, like Lido is like a really old one. I'm not sure anyone uses this before. And Inte loader, obviously it's Windows. Inte is the code Microsoft used for Windows NT. I think they call it new technology, Windows new technology, but that was actually before 2000. So you probably know this interface before. This is basically a GRUB loader, and if you want to have Windows and Linux or multiple different operating systems on the same disk in different partitions, and GRUB is a good loader for you to use. So like I said, systems like smartphones, PDAs, also game consoles, they usually store the entire OS on room. So the boot process is different. So execution directly on room is possible. However, running on room is usually slower, and that's why the CPU has the option to copy everything to the main memory. I give you a very detailed example how DOS boots. So when you power up your computer, actually Windows is the same thing, but it follows what DOS does. So the BIOS will first looks at the first sector of the hard disk. Then it will copy the whole 512 bytes to a specific location in RAM. So that location is hard-coded. It's always at 7C00 in hex. It's hard-coded. It always do this. Then it will give the control to that 512 bytes, because the first part of that 512 bytes are actually code. So it will simply set the IP. So how does it give control to it? Any idea? After it copies that sector into memory, how can it give control to it? Yeah, but jump to where? Just jump to that 7C00, right? Yeah. So then that the code in that first sector will start execution. So then that the bootloader will also that part of code will load the initial system files into your physical memory, and that file is called IO6 in the DOS system, and this file includes other files that load the remaining OS into the RAM. So you can see at the step 2, the BIOS will only copy one sector. It doesn't copy any more than that, just one sector. But after it gives control to the code in the boot sector, the boot sector can do anything it wants. So it can copy much more data into the memory. But the first step, only one sector, and it's always the same. So this is a very consistent approach. So no matter what operating system you are designing, you can trust the BIOS will copy one sector of that. So obviously the sys initial file will load other system files like Microsoft DOS.sys, and usually those are the kernel files. And after those system boots, the operating system will start load some specific applications. For example, the auto-execute.bat, that is for users to see. Yeah, go ahead.
Question, how does the BIOS handle interrupts? Like, for example, starting my computer, I press hold F12 or whatever the appropriate key is in order to gain access to the BIOS to change bootable drives or whatever.
So obviously, BIOS is like a very small operating system itself. So it handles interrupt just like how your operating system handles interrupt. But it doesn't have to handle everything at that stage. Okay. So usually users can specify what kind of applications or commands they want to execute when the Windows boots. So they can put in auto-execute the band file, something like that. And it's possible to have a dual boot, which is an act of install multiple operating systems on a computer. That is what the GRUB image shows there. So users, they can choose which operating system to boot. So something like this It's very popular like 15 years ago. So how many of you are still using dual boot in your computer, on your computer? Oh, really? Why don't you just use a virtual machine?
OS problems.
Okay.
Yeah.
Too slow or something?
Yes.
I see. I'm kind of surprised actually. Okay. So when you install operating system on our computer from scratch, so you need to create partitions, and there will be several partition tables, and usually a hard disk is denoted as something like this, HDA. HD means hard disk, and the third letter is which means which hard disk on the system are HDA. Usually is the first one, HDB the second one, and HDA 0 is basically the first partition on the first hard disk, and that partition is not really a partition, it's an MBR. It's the first sector, which is 512 bytes. And HTA1 is usually the primary partition. And a secondary partition may be created, and it can be further divided into logical drives. And here is an example. So we have a HDA 0, which is an MBR, HDA1, which is a primary partition. For example, we can have a Windows X there. Then the secondary partition, we can have multiple logical drives using different file systems. We can have FAT2 or NTFS, and also we can have Linux there. And usually Linux will use a special logical drive for swap. This is one example. So next, we're going to dig into the first sector of any hard drive. We will start with the code part. Then we will talk about the data part. So, like I said, the first sector, it's address, it's a three-dimensional CHS address is 001 on a physical hard disk. And offset 0, the beginning of this sector, there are some executable code. It can be as big as 446 bytes. It's not very big. But imagine what that code will do. It will just load other code, other sectors into memory. So it doesn't have to be so big. Then at the end of this first sector, there are several partition entries. So this part is called the partition entry table. And in this design, they actually only support 4 partition entries. So there can only be maximum 4 partitions. But the second partition, you can further divide it. And usually the last 2 bytes, there are some signatures. It's always the same signature, 55 in hex and AA in hex. So when you say something like this, it's very possible it's a bootable sector. So you don't have to remember those numbers, but you should remember there is a way to detect if this sector is bootable by checking those signatures. Obviously, even if the signatures match, you put 55AA there, doesn't really mean the code here is valid. But you're not supposed to do that. So there's a trust model. We trust the people who design those. If they put 55AA there, then the code here must be correct, and also the table, the entries are also valid. So anyone here play Texas Hold'em? Yes? Okay. So you know, if you play Texas Hold'em, this is a very good starting hand, right? The best hand ever. A 5-5 not bad if you hit a set. So I'm a heavy Texas Hold'em player. So let's understand the code first before we try to understand the data part. For you to understand the code, obviously, we need to understand some basic knowledge. I think you probably started this from computer architecture class or computer organization class, but I still want to go through this again. Actually, this information will also be very useful when we do malware analysis, malware forensics. So CPUs, in CPUs, there are a lot of registers and or register files. So but most calculations, they happen in those registers. They are super fast storage, but super small and super expensive. It's basically the first level of the memory architecture. But usually people don't say it's in the memory. When people say memory, they're talking about the main memory, which is RAM. But actually, everything like this, the registers, they are in the memory architecture, super fast to access. You can do all kinds of operations on the registers. So most architectures, you cannot do those arithmetic or logical operations on memory, main memory directory. You have to load everything to the register, then do all kinds of operations there. If you want to store it back, you put them back to the main memory. So here is the memory hierarchy. The fast we have is the registers. And after that, we have L1 cache, also L2 cache, and L3 cache. For Intel, usually there are 3 levels of cache to L3 cache. On most ARM architectures, only L2 cache. And usually, each core, because right now we are in this multi-core state, multi-core age. So each core, it has its own L1 cache. And several cores, they could share L2 cache. And all the cores, they can share the L3 cache. So all those cache, usually they are transparent to operating system designers, transparent to application developers. Usually you don't really need to, when you design a program in Java or Python, you never think about the CPU cache. But that is a major source for security issues, actually. So how many of you heard the recent security problem, Meltdown and Spectrum? So, yes. So, Meltdown, the main problem I see is it tries to optimize code execution. And so it is not, so the CPU does not faithfully execute what the end user wants them to execute. They will prefetch, pre-execute, and store those information in cache and also leave traces in cache. So this kind of hardware optimization, to me, they always opens door for some kind of side channel information attack. So we can infer what is in the cache and try to understand more about the information of a victim process or something like that. So in my own research, I do a lot of attacks at this level. So one of our research is about, so we're working on ARM architecture mostly. So ARM, one of the features we are using right now is called Trust Zone. It's a built-in security feature in any of your phones. So no matter you are using iPhone or Android phone, they are using ARM-based CPU, and that CPU has a feature called Trust Zone. So Trust Zone is the idea to split the CPU into 2 virtual CPUs. One is called the secure world. The other is called the normal world. So you can run your regular Linux, iOS, or Android in the normal world. Then run a more secure operating system in the secure world. So if you use Apple Pay, what happens is you put your fingerprints there, and all the information will go from the normal world, the iOS, to the secure world. But usually it's transparent to end users, so you don't really know what happens there. So obviously the communication between, the idea is the secure world will be more secure because not everyone can access it. So any application you download from the Apple Marketplace, they cannot directly access the secure word. They don't even know the existence of the secure word. So you put some information there, it's supposed to be more secure than you put in the normal word, put in your iOS or even your iOS kernel. So obviously, those two words, they still have to communicate. There are some special instructions for those two words to communicate. However, those communication can be monitored. The idea is there are limited ways for them to communicate, and it's easy for the system to check their communication. However, what we discovered is that even though those two words, they should be isolated. They should have a copy of everything. So each word should have a copy of system registers, all the system registers. We find out they actually share the cache. So because of they share the cache, we can do all kinds of tags. What we did so far is we built a covert channel between those two words. So any malicious program can steal information and try to steal information to another word. So this kind of a cache is a major problem for security now. It is there to enhance the performance, and it brings a lot of security issues. So after that layer, we have the main memory, and after that we have a hard disk. That is the speed for different memory hierarchy. So for Intel, especially x86, there are so many, not many actually, compared to other architecture, not many general registers. So this is basically all the general registers. They are 32 bits, and the newest version they have 64 bits. So the first general register is called accumulator, basically AX or EAX, and we can access the lowest 8 bits of EAX, and that part is called AL, and another general register is called BX. So basically EAX, EBX, ECX, EDX, those are 4 general registers, and part of it you can give it a name, like the ECX is like 32 bits. And if you only want to access the lower 16 bits of it, you will just use CX. So CX is usually used for counters. And when you program in C or Python, you don't think about this. But the compiler will decide which register the code it generates will actually use. And usually you will use ECX for counters. Yeah, go ahead.
Maybe from the slides why the accumulator and base go AHAL versus counting data go CLCH, L4H versus H4L.
Oh, that's just that's the same. That's just a typo. Okay. Yeah, the order doesn't mean anything. Yeah. So there are also some index registers under the Intel architecture. The most important is probably the stack pointer, and it points to the top of the stack. And EBP is also used to point to the stack, but how do I say this? Probably it will be. I will clarify this when I give an example later. Then SI is usually DI are the source or destination index registers. Obviously, SIDI is 16 bits, and the 32 bits version is called ESI or EDI. So usually they are used to point to the starting address of an array. So if you do some kind of memory copy, this is the register. Those are the 2 registers we will use. And there are segment registers, like code segment register CS. It points to the memory area your program instructions are stored. and DS, which is a data segment register, points to the memory area your program's data is stored. And in most cases, this is highly related to how you design your operating system. So as an application developer, probably you are not very familiar with this. So IP or EIP is the instruction pointer we discussed. It always points to the next instruction that the processor is going to execute. And there are flag registers, basically contain all kinds of bits set by different operating system operations. I think, so the assembly language class here, which architecture did you guys use? Intel or MIPS? MIPS, only MIPS? Okay. So MIPS is very similar to ARM architecture, but very different from Intel architecture. ARM and MIPS, they have a lot of general registers. Like ARM, there are 7 modes, and each mode has its own more than 16 registers, I remember. So there are, in general, there will be more than 50 or 60 general registers. But Intel architecture, there are not so many general registers. So we will talk about a little bit about the memory addressing modes. So the memory addressing modes, first is the amount of addressable memory is not the amount of physical memory in your system. This is called the virtual memory system. It is possible because there's a hardware called MMU. So everything your application says is in the virtual memory, not the physical memory. So it can be much bigger than the physical memory. Each process, usually they can say like 4 GB or even bigger memory space, but your physical memory can probably only 2 GB. Or if you have like you have so many processes running your operating system, each of them have 4 GB, that makes sense, right? So there's a hardware called MMU to translate virtual address to the physical address. And in x86, there are 2 modes, memory modes. The first one, the most important one, is called protected mode. So protected mode was, I think they invented that back in the 70s. It comes with a AT&T 86 CPU, and only in protected mode the MMU is used. Only in protected mode we have this virtual memory, and the virtual memory will be translated to physical memory when operating system executes. But when the system, so before that, before 80s or 70s, they only have this real mode. So everything your application says, everything the operating system says is the physical memory address. But to make all the operating systems compatible with old ones, so Windows, they still, the Windows or Intel, they still keep this real mode. And when a CPU boots, when your PC boots, it enters this real mode. So when your CPU boots, everything you see is the physical memory. Then it goes to, then it enables MMU, then we can see the virtual memory. So there are 2 assembly syntax popular. One is Intel syntax, another one is AT&T syntax. This is weird because Intel designed everything, but the AT&T syntax get very popular. The major difference is, obviously the instructions are the same. We're talking about the assembly code. So the assembly is basically cannot be directly executed. The assembly will be compiled into machine code for the CPU to execute. But at the assembly level, there are 2 different syntax. The Intel syntax, they usually put the destination as the first parameter. It will always move from the second place, for example, the move instruction. It will move from the second parameter to the first parameter, and the AT&T will move the source, the first parameter to the second parameter. So in this class, later we will use IDA Pro, and IDA Pro will use the Intel syntax. And most tools on Windows, they use Intel syntax. And most tools on Linux or Unix systems, they prefer the AT&T syntax. Probably some copyright issues. I don't really know what is the reason. So here's an example. This is an Intel syntax. So move EAX, EBX. Basically, this is copying from the content from EBX to EAX. Then there is another one is move EAX 10 in hex. That is move a constant 10 in hex to the EAX register. And there are several different addressing modes we will talk about. There is a direct addressing mode. So if you see an instruction like this with brackets, move EAX brackets 10H means copy the value located at memory address 10 in hex to EAX. So this instruction, the previous instruction, those two instructions, memory are not involved. We're talking about, we're only thinking about registers, and there is a constant value. So the constant, this constant is actually compiled into the instruction. So technically, so when those two instructions are executed, the CPU is not reading any data from the memory. Obviously, the CPU is reading the code from the memory. This code itself has to be in the memory. But in this instruction, the first instruction, the CPU actually reads the value located at that memory location to EAX. So, however, this instruction itself doesn't say that address is a virtual address or physical address, because it doesn't matter. That is the job of the operating system. That's the job of MMU. If MMU is already enabled, then that 10 is a virtual address. If we are still in real mode, the PC just boots, that 10 is a physical address. And we can have an indirect addressing mode as well. So even in the bracket, we can have a register. And we can even do all kinds of computations here. Combine several registers together. So something like this is kind of like trying to access an array. And also they can be the pointers. So something like this is also called a pointer. It's very similar to what you program in C. There is a pointer. And obviously the EAX, like I said, is 32 bits. So they are trying to read 4 bytes from that memory location into the EAX. What if you only want to read 1 byte, and this is what you do? You move to AL. AL is basically only 8 bits, 1 byte, and you try to read 1 byte from this memory location to AL. Give you more examples. So we have EAX here. The value is 20. EBX is also 20. ECX is 2. And those are the memory locations. And in this instruction, we're not reading the memory. We're only trying to copy BL to AL. So after this, obviously AL value will be the same as BL. This value will be copied to here. And this instruction, we will directly put this number directly to this EAX register. And this one, we are trying to read the value in the memory location 10 in hex, which is 12 in hex. Then we put 12 in hex in EAX. Like I said, AL is just the lower 8 bit of EAX. And this one is a little bit more complicated. We're trying to load the value at the memory location, which is specified in EBX, into EAL. So EBX, the value is 20H. So the CPU will go to the memory location 20H, find the value is 34H, then load that value to the memory, to the register. And a more complicated example like this, we'll just skip this one. Okay. So there are several instructions in the Intel architecture we can move data. So the most popular one is the move, just from source to destination. And this instruction, you can see that this instruction actually has several different forms. We can directly move between memory, between registers. We can move from register to memory. We can move from memory to register. But there is no instruction to move anything from memory to memory. So all the example we have, only one parameter can have that bracket. In this architecture, in this instruction set, there is no instruction can have both parameters with bracket. Physically, it cannot be done. So physically, there is no instruction to move data from one memory location to another memory location. If you want to move some data from the main memory location to another memory location, you have to load it to the register first, then move it. Of course, because of this, there will be performance issues. If we can do direct memory movement, obviously sometimes the applications they can run faster. So there are other techniques, for example, direct memory access, those kind of techniques. But there is no instruction to do that. That's beyond the CPU can do it. So some other physical device there to help. And there are some other data movement instructions like exchange or push, pop. Those are important ones to manipulate the stack. And also we have a very interesting instruction called a load effective address. So when we do malware analysis, the malware forensic part, you probably will see this instruction a lot. We will discuss this instruction later. So I guess you already know how this stack works, but I want to give you some examples here. So we have a stack here, and we have the stack pointer pointing to the top of the stack. Even though it grows down, but actually we call this the top of the stack. The image is not showing that. So if we are pushing, for example, this is the state of the stack right now. And now we have an instruction push this constant to the stack. Then the ESP will be changed, and everything, all the 4 bytes will be pushed to the stack like this. If we want to pop EAX, because EAX is 32 bits, the ESP will be changed, and those 4 bytes will be popped out from the stack. And there are a lot of arithmetic operations. Most of them are very easy for you to guess the meaning, and subtract, something like that. So when you see so when we do malware analysis, and also today, if you encounter some instruction you don't understand what it does, just Google that instruction with Intel. And there are conditional statements, conditional instructions, where they will execute based on the flags in the E flag register. Examples are, for example, test instruction, test EAX. It will always give 0. And test AL to this binary number, it will test if that bit in this register is set, and the compare instruction is a logical subtraction. Compare EAX, EBX, we'll just subtract EBX from EAX, then update the flags. So all the arithmetic instructions, they will affect the flags. After that, there are a lot of conditional jumps based on the status of flag. For example, jump E is jump equal. When you do test EAX and EAX, obviously the result is equal, then the jump will take if the values are equal. There are a lot of examples like this. We will skip most of them. Okay, here is something I want to show you. We have a very simple C code here. So this is an if statement, a variable A. We test if the variable A equals to this constant. If it equals to this constant, we will run this dummy function. So how compiler will generate the code based on this? This is the C code you write, and this will be the binary code generated by the compiler. Then actually this is a disassembly code. So what happens is it will compare the constant with A, but here A is actually a pointer. Compare that. If the value is not 0, it will jump to another location. If it is 0, which means A is equal to that, it will call this dummy function. And this here is a more complicated case. There are multiple condition if statement in C. So we are testing 2 conditions, and we test the first condition, then we test the second condition. If the first condition, because there is an AND, logical AND, if the first condition is not met, we will directly jump to exit. So we don't need to compare the second one. Then we compare the second one. If it's not met, then we go here. If everything is good, we call the dummy function. So this is how the C code will be translated into the binary code. If it's a while instruction, you can see it's very similar, except that there could be a loop. Because there is a loop, there is a instruction to jump back. So here is this location. So this one will jump here, and this one, this instruction, if A equals to that number, so it will always jump back to here. So that's how there is a loop. So this is how those condition instruction will be used. So I will show you another example how the stack works. So we have a function, a main function. The main function has in that function we have one variable, nothing, and we set the value of it, then return the value. So can someone tell me where that variable nothing should be stored? It's on the heap. Where should it be?
Stack.
Yeah, it should be a stack because it's called the local variable in the scene average. So because it's a stack, we want to see how it works. So first, when we enter that program, there will be a push EBP. So basically save the stack frame of the function that calls main function. Then it will move ESP to EBP. So it will set the current stack frame to the main function stack frame. Then it will sub for constant 4 from ESP. And this is making the space for the local variable nothing. So this is making the space on the stack. That is how that variable is actually on the stack of this main function. Then it will store value 0 to that variable nothing on the stack. So at the binary level, there is no symbols. In this code, you do not see the variable name nothing. that is only at the C level, the compiler will strip that away in binary code. So to find the location of that variable, it will use the stack pointer, the stack frame pointer of this main function, and it is because it was 4 byte offset to the pointer, so the compiler knows this is the variable location. It will store 0 to this memory location, which is the variable nothing. Then it will move the nothing's value to the EAX. So in Intel architecture and also C program, the return value is always stored in EAX. Then you will clear the stack and pop the EBP to restore EBP return and give the control back to the function that calls the main function. So now we are ready to look at the code in the first sector of the disk. So this is what I actually dumped from a hard disk. So this is the first sector of the hard disk. And the first byte is the first 400 or 200 bytes they are code. So the first byte is, so when we disassemble it, we get this disassembly code. And the first instruction is CLI. Anyone remember what that is? No. No. So here there's no interface. So give you some. So I means interrupt. So this is clear interrupt or disable interrupt. So like I said, because he asked a good question, how BIOS handle that, right? So BIOS will handle interrupt. That's how you can type things. But now, and there are also other kinds of interrupt directly generated by other hardware, and that could interrupt the execution of the program, and that is not what we want at this moment. So the first instruction is to disable interrupt. So we can make sure this piece of code will be executed without any interruption. So the second thing to do is move that constant 1000 in hex to AX. Then move that to a segment register, which is not that important at this moment. Then they will move the that constant to SP stack pointer. So basically that is setting up the stack for this piece of code. So if you are going to run any kind of C code, you have to, because C code, the compiler will generate code that uses stack. So before you run any kind of C code, your operating system has to set up stack. But at this moment, we're not told, there's no operating system, this is just a bootloader. This is a way low level than that. Then move 0 to AX and move 0 to DX. So the DS value, the data segment will be 0, the extra segment, I think, ES will also be 0. Basically set them, those two registers are 0. Then after this, they feel it's safe to enable the stack. So this is, enable the interruption. So this is a set interruption. Then move this value 7C00 to SI. Anyone remember what is 7C00?
Location of the root record?
Exactly. So what is this piece of code?
It's moving the stack. It's
No,
it's putting the address for the bootloader into SI.
Yeah. So this piece of code, where is it right now as a memory? It is at this location, right? It is loaded by the BIOS to this location. And now it is setting this value to source index and set this value 600 to the destination index. Then CX is the counter. Set CX to 200 in hex. What is 200 in hex? So 200 in hex is actually 512 in decimal. So that is the size of the first sector. It's the size of the sector itself. So what it's going to do is it's putting the this address itself's location to source index, and the destination address to the destination address. Then it's going to repeat move. This is a byte. So it's going to repeat how many times? 512 times. So these 4 instructions are actually moving this piece of code to another direction, to another memory location. It's moving itself to another memory location. So after this, it will do a jump. It will jump directly to its new location. So this one. So this one is 1C. So you will directly jump to 621. So which is the new location for the next instruction. So the next instruction offset must be 21. So you can see the first line there. The next instruction's offset is 21. So when we execute move 7BE to SI, we are not executing this at 7C21 anymore. We're executing this at 621 in hex. Then this piece of code will do all kinds of other checks. And what I want to show you next is here. It tries to read, basically they are going to check all those MBR records and try to node another. Basically this piece of code, the job is to node the next level of bootloader. And to do that, they are going to node that from the hard disk. And to node from hard disk, they have to use the interrupt instruction, int 13 in this case, to read a sector. So there is the move instruction. It cannot directly read from the hard disk. That's why they have to use the Inte instruction, because the hard disk is not part of the CPU. The Inte instruction makes the CPU to talk with some peripherals. In this case, is the hard disk. So this is basically the piece of code in the first sector of any hard disk. It could be slightly different, but almost the same. And you can see we said there are 400 bytes available, but this piece of code only uses 49 in hex, probably 60 or 70 bytes. Any questions so far? No one is following? Okay, so let's take a 10 minutes break. Then we are going to move to the data part.